All right, and we are on the air. Hello, friends. Welcome to Codementor Office Hours for today. My name is Mark. We're really excited to continue our JavaScript framework series today. We've been doing a whole month, and we're actually going to keep going for the next couple months on JavaScript sort of centric office hour sessions. And we're thrilled today to have Zach Nation joining us. So I'll give Zach a brief introduction, and then I'm going to kick it over to him for a presentation. But if any of you are new to office hours, if you're in the live room with us, please feel free to use the group chat to throw any questions you have in, or if you're watching the asynchronous video in the non-live room, there's a Q&A app you can use, and I'll be monitoring that the whole time to sort of collect questions. So feel free to jump in with questions whenever you feel. But without further ado, Zach Nation is a software engineer at Dado, previously called GraphLab, which works to help data scientists create predictive applications. He was previously a senior software developer over at Microsoft. He holds a degree in computer science from the University of Arizona, and Zach is currently joining us from Seattle. He's going to walk us through some scalable data visualization techniques in React. So everyone on mute, welcome Zach Nation, and Zach, I'll kick it over to you.
Okay, thanks, Mark. Hi, I'm Zach. I'm really excited to be here today. And without further ado, I'll get started talking about some data visualization stuff. So I'm going to go ahead and share my screen and present a set of slides. So first I want to talk about us at Dado and how we use React.js. So I work at Dado. We used to be called GraphLab. We are a venture-funded startup in Seattle, and we're working on challenging problems in data visualization and machine learning. So really trying to help people have an easier way to do exploratory data analysis all the way up through building machine learning models and deploying them to production. And my area of focus is on the data visualization side. So I work on a part of our product that we're calling GraphLab Canvas. This is a large-scale data visualization tool. So a lot of visualization tools out there are really built to handle kind of Excel-sized amounts of data. We're looking bigger than that. So we've actually loaded up as much as several terabytes of data into our data structures. We call that S-frame. For scalable frame. And GraphLab Canvas is designed to be able to display data from an S-frame of any size. So I'm really excited to talk today about some of the techniques we use to do that in the browser with React.js. So just to give some context for what we're doing, when a user is building a predictive application, or a developer is building a predictive application, there's kind of a set of 4 steps that you have to go through at a high level. The first one is to understand the data, pick out some relevant. Second one is to pick out relevant information. Data scientists will call this feature engineering and feature selection. The next step is to build a model, which essentially involves taking some machine learning algorithm and training it on the existing data that you have using the features that you've selected. And then deploying the model involves basically a production lifecycle. This will be very familiar to any web developer, where essentially you're taking something that you've developed on your machine, deploying it to production, and you have test infrastructure and monitoring and things like that to make sure it's working and behaving the way that you expect. And so throughout that whole pipeline, data visualization can be a really important tool to helping you understand everything from what's in the data itself to how you're manipulating that data, how a model is working and performing, and then how a service is working and performing in terms of things like latency and throughput. So we use the same visualization platform everywhere. Why are we doing data visualization? It turns out that human beings are really good at visual pattern recognition. There are just a lot of types of data, data sets, and then shapes of data, essentially, where looking at summary statistics does not give you a very clear picture of what's actually going on in the data, but visualization can immediately give you that picture without having to dig too much deeper or spend too much time on it. So it's a very quick way to get an understanding of the shape of some piece of data. The example shown here is called Anscombe's quartet. And this is the classic example in data visualization of why visualization is necessary in the first place. As you can see, each of these examples has the same summary statistics, but clearly they are very different data sets. So that's just one place where visualization is a very important tool. So I want to show a real-world example on Bitcoin transactions. So this is a larger data set than you could typically fit in a browser. So I think it's representative of the types of challenges that we're facing. It's sequentially arranged, which means we can visualize it while streaming the data through. This is helpful for the particular demo that I'm going to do. That is not always the case for data that you're dealing with. So later on, I'll talk more about how to deal with data sets that are arranged randomly or that you can't make any assumptions about the order of the data. And I also think this is a data set where visualization might reveal some interesting patterns or information that we wouldn't get by looking at summary statistics. So I started out by just opening up the Bitcoin blockchain in my trusty hex dump just to kind of see what was going on in this file. As you can see, there's some ASCII characters in here. It looks like a small description of something inside the blockchain. For the most part, it's binary data, so it's hard to make sense of, but I did start to notice a pattern. This repeating, it's actually F9BEB4D9. That's actually the magic header for each block in the blockchain. So the Bitcoin blockchain is essentially one long array of blocks, and each block represents a set of transactions on Bitcoin. So it's a giant public ledger that everyone writes to by performing transactions, and all of the data is stored sequentially here and can be parsed out. So I actually wrote some JavaScript code to parse it, loaded it up into GraphLab Create as an S-frame, and got some really useful display of what was actually going on in that file. So we have about 45 million rows. This has now been parsed out into individual transactions. So we have transaction numbers here. Each transaction has a timestamp and an amount. There's some other data as well in that blockchain that I did not include here just for brevity. But essentially, you can think of it as a long list of transactions and transaction amounts. And of course, each one has a to and a from address, but I didn't include that here. So I want to give a short live demo of what those Bitcoin transactions look like. And I'm actually just going to run my local copy of this demo code. For those who want to follow along with the code at home, this is actually on GitHub as github.com/znation/scalable data visualization. So that's the name of this talk. This is the same demo and the set of slides that I used at React.js conference, but I'm going to go into a lot more depth here about how to actually structure the code, how to do data transfer between a node server and a React application with a large amount of data like this, and how to use D3 to contribute information to a React component, but still use React for rendering. So that's all the code is in here. The bin directory is kind of just output from the build, so you can look in source and get an idea of what this thing is doing. So I'm going to actually show the demo here. So this is just a small component I built to show the total number of Bitcoin transactions per day over time. And here's where it helps that the Bitcoin blockchain is arranged sequentially over time, because we can stream through the whole file in a single linear pass and not have to do any kind of more complicated transformation to get a good visualization out of that. So what's happening here is I have a node server going in the background that's processing this blockchain, and it's actually going through the raw blockchain parsing binary using node binary. And what I've got here is a histogram essentially showing the total Bitcoin transaction amount per day. So we're binning on each day and then drawing a bar for each day that happened historically. And then at the same time, we have a history log here, which will update over time as we move into the future in the blockchain. So for that, I found a wiki page that detailed the history of Bitcoin, and I just took down what was the date on which each event occurred. And in my React component, I am filtering on the max date of what's being displayed here to know what to display in this component as well. So I'll show the code for that. As you can see in this demo, there's some really interesting correlations between real events in the blockchain and large spikes in the transaction volume. So when you look at like the exchange rates being published, that correlates to a really big spike because that suddenly indicates to people, now I can trade Bitcoin for real dollars. So now, and actually that's an incredibly good exchange rate. I wish I could go back in time. So you can see actually real world events do correlate to changes in transaction volume, and that's something visualization can tell us much more easily than if we were to try to just look at the raw data or summary statistics to get the same information. So for now, I'll close that and I'm going to go back to the presentation. So what are some of the challenges involved in visualizing such a large data set? The biggest challenge is probably just condensing that amount of data into a smaller set of visual elements. So we're starting with over 20 gigabytes of raw data. Clearly we can't ship all 20 gigabytes to the browser, so we have to have some architecture that lets us do that data reduction and aggregation on the server, and then send a smaller amount of data to the client to render as visual elements. What I mean by visual elements is anything that shows up in a plot, including maybe that history ticker, but especially access data, labels, and all the data points themselves that are showing up in that plot. Another challenge is maintaining a high level of interactivity and performance while doing this kind of computation in a streaming fashion. And then another challenge is to maintain the interaction state across the whole application UI and controlling some server-side long-running computation based on that UI state. I'm not going to get into that challenge too much, but that's a big challenge in a generic platform that we make, GraphLab Canvas, for data analysis in general, because if you're switching back and forth between large data sets, now you have to manage essentially what's in RAM on the server based on the UI state on the client. And we have an architecture where your server is running on localhost. So you can think of it as one big application spanning across a network, really just for, you can think of that as an implementation detail because the whole thing is one application running on your machine. But it turns out these are actually the things React.js is good at. If you look at rendering visual elements, maintaining interactivity, and then keeping track of state, these are actually the things that suddenly became easy when I started using React.js. So that's when I realized it would be a good fit for data visualization problems. And now that we've been doing this for about a year, I think it has been a good fit. So I'm happy to keep doing it. And I'm glad to tell the world about how we're doing it. So looking at kind of the data visualization pipeline, how do you get from raw data, like that 20 gigabyte blockchain, into a rendered visualization, which is really the DOM and styles and everything that show up in the browser? What do you have to do to get there? The first step is aggregation or data reduction. This involves essentially taking that data and turning it into a smaller amount of other data that will represent the plot more directly. So we're not really plotting 20 gigabytes of data here. Most plots can't really accommodate that much data to begin with. Everything involves some kind of aggregation or reduction in order to give some other visual result. I don't think as humans we're really capable of looking at, say, 20 million or 40 million unique points of data anyway. So this is a critical step in understanding what's in that data overall. The next step is taking that aggregated or reduced data and turning it into a set of visual elements. This means going from a block of data, like in an array of numbers, into things that we can think of as axes, tick marks, labels, width and height of bars on the screen, for instance. And this is something that D3.js is traditionally really good at. So I've always been a big fan of D3, and it's a huge tool belt library for visualization in JavaScript, and it's sufficiently low level to let you express whatever you want to express to craft any visualization you want to. And there's a lot of really good toolkits in there for things like scaling that make you not have to reinvent the wheel as you're constructing visual elements out of aggregated data. The next step in this pipeline is rendering. Here, a lot of people use D3.js as well. It has its own data binding solution. Although considering we have a larger application in React.js, I prefer to use React.js for this rendering step as well. Rendering here, I really just mean taking and then putting them on the page as SVG or as a canvas element, and doing data binding, at least in the case of SVG. Neither D3 nor React have a really good abstract way to do data binding to a canvas element. But canvas is essentially an immediate mode UI anyway, so you can just redraw the whole frame every frame if you need to, assuming it doesn't take too long, or you may have to micro-optimize. So what is that first step of aggregation or data reduction? So you have to kind of design and optimize a data pipeline to get something like 20 gigabytes of data, or even 200 gigabytes or 2 terabytes into a form that you can ship over to a browser. So the first principle you have to follow is compute close to the data. You can imagine it this way. You have a very beefy server with a huge amount of data on it and a really, really tiny pipe to a web browser. That web browser is where everything is ultimately going to get displayed, but you can't just ship over all of that data. If you were to try, it might crash your browser long before it all gets there. So always compute close to the data. Do the data reduction where the data is. To accomplish this, we use an architecture that is Flux-like. So I've copied the Flux architecture diagram from Facebook's Flux overview site. And as you can see, essentially, I'm sure a lot of you are familiar with this. You have a dispatcher and a store component that are responsible for, dispatchers responsible for taking actions and making changes in the store. The store is responsible for being the single source of truth about state, essentially. And everything flows from the store into the view, which actually renders on the page. And this helps you keep track of state changes throughout the whole application. We use a very similar architecture, but we've actually replaced the dispatcher with an XML HTTP request and or WebSocket. So essentially, we're crossing the wire over the network for every action. And our store is actually a stateful object on the server, which, unlike most Flux implementations, this simplifies state management quite a bit, because we don't have to keep anything in sync across the client and server. Everything goes to the server, and the server is the single source of truth. This works because our application is on localhost, so this is not necessarily an architecture I would recommend for, say, an internet-facing application. But if you are building something that reads off of local disk and then is rendering in a web browser with a server on localhost, this could be a good architecture, and it's been good for us. So what does it mean to do scalable aggregation? So some of the types of data aggregation we do are binning. If you're doing binning in one dimension, you get a histogram, which is essentially a bar chart of, it's almost like pivot tables, if you've seen that in Excel. You can count items into ranges, and then you display the number of items that fall into each range. So here's a visual example of that. We've got equal width bins here. The first one has 1 item, the second one has 4, and so on. And you can see, essentially, you just count them, and then you have bars whose height is represented by the count of items in each bin. So that's a histogram. And you can see that this is an effective data reduction technique, because now we have 5 data points where we used to have quite a few. If you do this in 2 dimensions, you get a heat map, which is essentially, you can think of it as a scatter plot. It's a 2D plot, so typically 2 variables or two columns in the same data set plotted against each other. And with a heat map, you're using color to represent the density of points in each region. Another technique we use is sketch data structures. The general idea of a sketch data structure is that with a linear complexity, algorithmic complexity, so 1 or maybe 2 or 3 passes over the data, you can get in some cases, some accurate statistics, and in other cases, some approximate statistics or approximate results. And you can do so in a streaming fashion, which means you can start rendering the visualization before the sketch is complete. And that's key to everything we're doing in GraphLab Canvas, because one of the principles in developing this is that we don't ever want to make the user wait. When you're dealing with large amounts of data, if you're doing everything as batch processing, you could tell it to do some data reduction, come back 15 minutes later, you've totally lost your flow and you've been interrupted essentially by your software, and that's not a user experience that I would want to deliver. So the principle that we like to follow is everything we do streaming and with immediate results, immediate partial results. There's been some great academic research in this area in visualization as well, so we're inspired by that, and I think we've been giving good results here. So I'll talk about some of the techniques we use when I show the code there. So overall, if you're doing scalable aggregation, you want to have constant or very slowly growing memory complexity, because part of it being scalable is you don't know how big this data is going to be in advance. So you don't want to scale linearly or worse with the amount of data on memory. And you want to produce results incrementally. That, again, is key to the user experience, not making the user wait too long. And you want to send results to the client periodically, not constantly, because you'll overwhelm rendering for no particular reason. You could be re-rendering 60 times a second, but I don't think that's actually helpful to the problem of visualization, and it's just going to eat a lot of CPU. So I wouldn't recommend it. Here's a small diagram of just how we do this. Essentially, we're aggregating in chunks over the data, and then occasionally, not every chunk necessarily, sending data back to the client. So here's an example of server code that's actually sending data to the client, and we're doing this every 100% of blockchain. That's just some arbitrary metric that I decided was a good way to decide when we're ready to send more data. In practice, this results in about every few seconds sending a new batch of data to the client. And then in the meantime, the server is running uninterrupted, just processing all the blocks. So you can see actually that for loop up above is taking transaction amounts from each block and adding them all up, and then that's getting sent down to the client. Similarly on the client, we're actually receiving in a WebSocket from where that server was sending. We're receiving a message, and this is a JavaScript typed array, and so I'm just passing it directly into the hist function, which is a function that I wrote. It's not shown here, but that will take that and return an object representation that we can then query from a React component. And I'll get into the code on that as well. The next step here is describing the scene graph. This is taking that aggregated data and turning it into a set of visual elements. So again, what do I mean by visual elements? Here's an example of a plot from GraphLab Canvas. There's kind of a lot going on. Visual elements is each individual thing here. So we have a plot title, description, axis label, ticks and tick labels, all of the individual data points themselves, and plot controls and summary statistics. All of these are visual elements. They're, if you think about how you would break down a React component into subcomponents, each subcomponent and each subcomponent of those could be a visual element in this. So something that makes visualization a little different from typical React components. In a React component, the text values are typically data dependent. but in a visualization, these sizes and positions of elements on the screen are also usually data dependent. And to know those sizes and positions, this is where D3.js really shines in combination with React. So I'll get into that a little bit here. D3 is an interesting library. So it's kind of a do everything visualization library in JavaScript. It's got a core set of functionality and then a bunch of namespaces within as well. And I did kind of an inventory of all the different parts of D3, and what I discovered is that almost all of the parts, as you can see highlighted in purple here, are actually are either pure functions, idempotent functions, or something close to it. Maybe objects that are stateful, but you can query them for results. So all of these are usable from within a React component without any kind of jumping through hoops. And so I've gotten a lot of mileage out of D3 in combination with React that way. You'll notice that selections, transitions, and drag and zoom are not included on that list. These are the parts of D3 that are really specific to data binding. So if you're using D3 to do rendering, those would come into play as well. And I've seen a number of techniques that go that direction, where you have essentially a leaf node React component in your tree, and then you have a D3 component underneath, if you want to think of it that way, where D3 is doing all the rendering, and React just hands off data, and you can use the lifecycle methods like shouldComponentUpdate to make sure that React will not touch the DOM after that point, and then it won't be concerned about the DOM underneath that component. But here I'm going to show the technique I prefer to use, which is to use React to actually do the rendering to an SVG DOM tree, and I'm using D3 to do all the computation. So here I've defined a React component called axis, and what I'm passing in as a property to it is scale. Scale is actually a D3 scale object. So I'm calling d3.scale.linear here. I give it a domain and a range, and then D3 gives me back a queryable object for a scale from that domain to that range. And this is great because I don't have to implement scaling now. And so within the child component that gets that as a property, you can see I can use scale.ticks to get a list of ticks, and I can just map right over those and then return, oops, sorry, technical difficulties. Okay, back to here. Sorry about that. You can see I just use the scale function on each tick. Again, this is just the D3 scale itself. And now I can return from my React render a list of SVG group elements with a line and a label on each one. And this is a tick line and a tick label. So this overall is going to give me a list of ticks. And then React is doing the rendering, which means you get all the virtual DOM goodness. So how do you choose a render target? What are some possible render targets? SVG, Canvas element, and React art are common ones. With React, there's a lot of possibilities. You could even do things like WebGL, XAML, Direct2D, iOS and Android, especially now with React Native. Just to keep things nice and simple, I'm just going to talk about SVG and Canvas. React Art is a great abstraction layer on top of SVG and Canvas, but what I've found is that when I want to use SVG, I really want the specific features of SVG itself, which means I want to use CSS styling on it, I want to use DOM events, and React Art is a little bit more limited there. And if I want to use a Canvas element, I'm going to use the Canvas element directly and bypass React Art as well. And usually you can decide up front based on the characteristics of what you're rendering which one to use. So what are the considerations you would use for that decision? That's the number of visual elements you're rendering, the amount of animation you want to do, the level of interactivity that you want to support, and browser support. Notably, React Art has support for IE8 rendering with something other than Canvas and SVG. I think it's VML, something like that. So if you're not targeting IE8, then you don't need that. So looking at just SVG and Canvas, what you get from SVG is the ability to use CSS styles, CSS animation, and DOM events. This is really powerful because you can use the full power of the browser, just like you normally would for an HTML DOM with divs and spans. But you get a really graphic-specific language to talk about it in, with things like groups and rectangles and different kinds of shapes. If you have 1,000 or fewer visual elements, then I think you'll get reasonable performance out of either SVG or Canvas. So I think for smaller applications, it's fine to use SVG. For types of plots where you don't have to draw too many things, if you're drawing bars across a single dimension of data, that's very reasonable to use SVG for that. Where the Canvas element comes into play is if you have more than 1,000 or so visual elements, I've found that you can really slow down the browser rendering a lot of SVG elements to that. So heat map is a great example for Canvas, where if you want to have a heat map across 2 dimensions and you want to have, say, 500 bins in each axis, then you're dealing with 500 by 500 rectangles, which is way too many DOM elements for the browser to be able to handle with good performance. So there I would draw to a Canvas element where you can get good performance. And in doing so, you will give up on some of that DOM goodness like CSS and events. So what is the data visualization architecture? This is what we use in GraphLab Canvas. It's 100% React.js rendered with a stateful server. We use a streaming sketch data structure to perform aggregation while visualizing. And we've tested this with up to about 1 terabyte of data. This is old, actually. We've now gone up to closer to 10 terabytes. And responsiveness and performance remain roughly constant as the data size increases. So every technique we're using scales to any amount of data. And here's just a good diagram overview of this kind of architecture. So we've got a stateful server and a web browser displaying results from that server. We have a constant streaming aggregation step going back and forth here between our state object, our store. The store is feeding data into the React component. The React component is sending updates to a dispatcher on the server, which is sending updates to the store. On the browser side, we're rendering to either a Canvas element or an SVG element, primarily determined by the number of visual elements for each plot. And again, that's a determination that's specific to the plot type. So I'm going to go ahead and jump into live coding on this demo itself. Again, the URL is here if you want to follow along with the code. And I will go ahead and jump into that now. So here I have, I'll make the font size a little bigger here. Here I have the main client-side component for this demo. This is the same demo I showed earlier with Bitcoin transactions. I've got React and WebSocket module here and a few of the React components I've written here. The histogram component is transactions by date. This is just that bar chart that we saw, live updating from data. The history component is the ticker of events that happened in the past. And then I've got some configuration and the hist function, which is a wrapper around the raw data that comes back over WebSocket. And so I'm going to make an improvement to this demo, and I'll show you how I do it. So what we can see here is it takes a second to load. That's fine. So when it first loads, we get a few history items here. It's still crunching in the background. And as it updates, it's going to render more bars here, slide them over, and it's going to add more history items here and slide these down. But what I really would like to know is which bars correspond exactly to which history items, because it's a little bit hard to tell. So what I'm going to do is plumb through some state in this React component that can know what I'm currently hovering on with my mouse and highlight both the bar down here and the bars up here that correlate to each other. So this is actually, this is kind of what's known as like a cross filter or a cross component state in visualization. I'm getting some font weirdness here. Okay. So in this top level component, which I'm calling dashboard, I have component state that is currently keeping track of, actually active tab is bold. I don't think I'm using that anymore. I can get rid of that. I don't have tabs here. The state that I do have is the actual data coming back over WebSocket. So I start out with an empty array of the right size for that histogram. And then on message received over WebSocket, I'm just going to do set state, and I'm going to set that histogram to whatever message actually came back. So the server is responsible for constructing a typed array representation of this data, and then pushing it to WebSocket. And again, I picked a threshold that seemed like a good threshold for that, and it's at every 100th% of Bitcoin blockchain. So every few seconds in practice, this is coming in with more data. But I think we need a little more state in this component to be able to represent where I'm hovering with the mouse to be able to correlate individual bars here to this here. So I'm going to add a piece of state in this component state called hover date, and I'm going to set that to null just to start with. And then what I can do here is I'm going to add a function on hover that takes a date. And what I'm going to do here is this.setState hover date date. And that way we will be keeping track in this component state of whatever date is being hovered on. And now I'm going to pass that in as a property to the history component. And I'm crossing that 80 character column mark. So I'm going to just restructure this to look a little bit nicer. So now I have a function being passed into my history object, and so I can use that in here from props. So here I've actually just hard-coded a list of events that I got from Bitcoin Wiki history. And what I can do is on hover for each history item, I'm not sure I remember the event to use for this. Try on mouse over. And I'm going to bind to that the date. And then just to make sure this is working, I'm going to log here the date itself. So now what we should see when we load this, and I'll open up the console. What we should see here is whenever I hover over a list item in history, we should get an event. Uh-oh. This is always, live coding is always dangerous. Cannot read property bind of undefined. Oh, okay, that makes sense. Because that should be this dot props dot on hover. That came in as a prop on this component. Right, of course. So let's see what that looks like now. And as you can see, as I hover over these, I'm actually getting the date out of these components. And that's getting stored as state on that top level dashboard component. So now let's go use that to highlight one of these bars. First, let's see if we can highlight the date itself. See if we get an interesting result here. So what I'm going to do is let's see what happens if we set the background color of that list item to something more interesting. That's a little terrifying. There, I think that's better. So we're going to set the background color to that purple, and we're going to set the text color to white when we're hovering over that element. You restructure this component. So what did I call this? Hover date, right. So if this .props.hover date is the same thing as the date for that item, then I'm going to make this purple, otherwise it's white, and I will make the color correspondingly either white or black. So this is just going to set a style on that element for each list item here, depending on whether the date is the same date as the hover date being passed in. And so we'll pass that hover date as well. And so in this component, it's state because it's local to the component. Since I'm passing it into the child component here, it's coming in as props. So that way there's always a single source of truth about where the data, who owns the data versus who's just getting told what it is. And so if I reload this, what I should get now is as we hover, we can change the rendering here, and that's working. So you can see whatever date is being selected in that top level dashboard, each list item as I hover is changing to that color. And so let's now try, I want to set on mouse out as well, because right now it's getting stuck. If I mouse over and then leave, it's still the same component. So I'm going to say on mouse out equals this.props.onHover.bind, and we're going to bind null null. Null is that first null is the component that it's going to run on. Since React is already binding its methods to the component they're defined on, we can just pass null here, and the binding that was already set will work. The parameter binding I'm using here, null, will just reset that state to not have a particular date. It'll be set as null. And so now looking at that here, we can mouse over and then mouse out, and it'll get set back to null. So now all we have to do is plumb that through into the histogram component itself so that we get a color on hover there. So let's do that. And this is transactions by date. And here we've got some axes and then a set of bars. So on the bars, I'm going to pass hover date equals this.props.hover date. And then on bars, so for each date here, we've got a rectangle. And then I do need some code to actually figure out what the date is in each of these. So this value is, the value is what's on the y-axis. The date is going to come from the x-axis. So that is the relative position on the x-axis to the first date in the data set. So actually this will require a little bit more plumbing here, because right now each value here doesn't actually know its own date. What we can do is, let's go back up to the component above. We have, at the top level, we have dashboard that has a histogram with a set of data in it. That set of data is in transactions by date here. And so that has some utility functions that I've written. Get bin, and then that's finding a bin relative to the minimum date value. So let's take a look at what those values actually look like. Maybe there's something here we can use. So this value is 50, and then the position is 0. And that position is very relevant because that's what we're going to use. Next value is 0 and its position is 1. Yeah, so for each of these positions, I realize this is, the index is 1 per day. So we're actually just adding days to the first day in the data set. And the first day we can get from data.getBin. What is this? No, data.domain, I think. Let's put a breakpoint here and take a look at data.domain, because I think that will have the date that we need. This is getting very slow. I'm just going to restart it now. For some reason, I think I have a memory leak in here. So let's just start that over again, and I'll open up the inspector, and we can see we should get a breakpoint now where we can look at data.domain. So while that's loading, I'll just make sure we have that breakpoint. So this is a debugger statement on the outermost component for the histogram right before we render. So let's take a look here. So data.domain has something that looks like Unix timestamps. And if we look at the timestamps here as dates, no, that's not quite right. Well, actually, I think it is. That's for the particular set of data that's come in so far. If we keep going and look at the next time we render, we should have a bigger domain because we'll now have processed more data, and we do. Yeah, so this is correct. We're starting at January 3rd, 2009, and then as it streams through, it will go all the way up to the present. So what we want to do is take that date and calculate based on the index into this set of data how many days have passed, and then based on that, know whether to highlight the item. So what we can do is in the outermost component here, let's go back up to dashboard, and we can say hover idx equals, and then we can just use a JavaScript expression here to determine the index that we're going to highlight. So let's call that highlight idx. And this is going to be so let's suppose we had something like that. That's not quite what I expected, but let's... So this, I think, is the number of milliseconds between those two dates. So if we divide by 1,000, we should get number of seconds. Times 60 should give us number of minutes. Times 60 should give us number of hours. Times 24 should give us number of days. And it looks like it does. So let's take highlight IDX and say it's going to be this.state.hoverdate minus this.state.data.domain. I'm going to put that in a date, new date. This.state.data.domain 0 is the first date. That's the minimum date in that data set. And we're going to divide that by 1,000 times 60 times 60 times 24 to convert from milliseconds into days. And so let's see if we can now go into the transactions by date here and pass that through to bars. So we actually don't need hover date there. What we need is highlight IDX. So we'll pass this .props.highlight IDX. And so now into this component, we have the index of the bar that should get highlighted. And now all we have to do in bars is say this.state.highlight IDX. Sorry, that's props. Props.highlight IDX equals IDX. Then we're going to do B0007F. Otherwise, we're going to do that one that we were doing before. So now what we should get, and we have to remember one more thing, which is that this is going to return a floating point number. So I'm just going to do a math.floor to convert to an integer, since those indexes are integers. So we'll start that server over again and start at the beginning here and see if we can cannot read property domain of undefined. Let's try that one more time just to debug here. So this .state.data is undefined. That's because it's called histogram. Okay. Well, let's call it that. So now let's see what we'll render here. I think probably I'm not sending the right index in. It may be that floor was not the right rounding function to use here.
Hey, Zach?
Yeah.
Yeah, it's been great. Since we're down to the last few minutes, I just want to see if we'll open it up maybe for some questions.
Yeah, that sounds good. Yeah.
Awesome.
Here, well, I'll just conclude with the implementation of that index. I'll leave as an exercise to the reader. Sorry we're out of time, but I'll actually finish that up and post it to that GitHub repository so everyone can see the solution after this talk.
Cool, and we'll send out a link to the GitHub repo to everybody. Sorry, I'm getting a lot of echo. Yeah, so if anybody has any questions, feel free to shoot them in to the chat or the Q&A app. Otherwise, I can start off with a couple that were emailed in to us. So I'll go ahead and do that.
Okay.
So Walt emailed in, who actually this is a pretty representative question of what a few people were wondering. Could you comment on, in regards to the visualization solution stack, where does, in terms of using React as a component of visualization, what are the pros and cons versus other JavaScript frameworks? So this person is an Angular developer, and he wants to know why React as opposed to another JavaScript framework for visualization.
Okay, that's a great question. Yeah. I think a lot of JavaScript frameworks actually would be a great fit for visualization. Typically, historically, visualization has been kind of seen as a different problem space from web application rendering in general. But I came from a more general web app background and got into visualization, and I started to understand that they're actually very similar problem spaces. So really the core problems around both are state management and data binding. So I think a lot of JavaScript frameworks do those things really well. Those are really the core problems that modern frameworks are trying to solve. And so I got into React and enjoyed using it. I wouldn't say that it's necessarily the one right choice for data binding and rendering in general, but it's been a really helpful framework for us to use. So I'll give a shout out to Angular. I know people have been doing visualization in Angular with a lot of success. I think Ember would probably be a fine choice as well, and I've seen people using Meteor as well. So
one follow-up question there, something sorry, the echo's kind of nasty. Really quick. With all these, we've been doing a heavy focus on JavaScript in these office hours. So, what are the variables that help you pick React when you were getting started, on this specific path?
The answer to that is simplicity. What drew me into React in the first place was the small API surface, the simplicity of concepts. I think the idea that any new developer we've even had people on the team who are both new to JavaScript and new to React, can jump right in and start being productive in our code base because of the separation of components that React naturally gives you as you express things in terms of React components. So I was really inspired by Pete Hunt's talk on rethinking best practices. What I've found is that separating components rather than traditional web app concerns really gives cleaner architecture and lets new people jump right into the code base.
Awesome. So Sam, I'm pasting in. Actually, I just found a link to that talk you mentioned. Sam just jumped in with a good question. Do you recommend any resources for someone who's familiar with D3 and wants to get started with React? On that note, I almost think we could expand the question. Resources in general for getting started with React would be helpful. Oh, I think you're muted. Oh, Zach, I think you're muted. There you go.
Sorry about that. Yeah. There's a blog that I've been following from James Long, I think it is, J Longster, and I'll see if I can find it and paste the link in. So he's written a great series of articles on sort of using React to its fullest potential, and some of these were really helpful for me when I was getting started with React, so I will see if I can send a link to that. I'm not that familiar with the Google Hangout UI.
Oh, it's in the left side. There's a little chat.
Okay, so his blog is there. The latest articles there are going pretty deep on build tools and things like that, but if you go back a ways in that blog, let me find the post that I first read that got me into that. Yeah, okay, here's one. But yeah, I would really recommend especially James Long's whole blog, but especially that post.
Awesome. Yeah, well, Roman, hopefully that addressed a little bit of the recommended blogs to check out to get started. Unfortunately, we are out of time. I don't want to take up any more of Zach's time, but thank you so much, Zach, for walking us through getting started with visualization and with React. And for everybody watching, this is going to be posted on the Codementor YouTube channel, so definitely we recommend reviewing this. I know it's the kind of thing I would want to watch a couple more times to really digest. Zach, where else can people check out your work or follow you on Twitter?
I'm at Reverius42 on Twitter. That's Reverius 42, and I'll paste a link to that in as well. Of course, you can check out Datto.com. Which is the company where I work. We're working on really cool visualization and machine learning stuff, and we're hiring as well. So check us out, and I'll paste in a couple of links here.
Awesome. Yeah, thank you guys so much for tuning in, and obviously if you're working on any React projects and need assistance, feel free to use Codementor anytime. And we'll see you next time. Check out some more office hours coming up. There's more great ones this week.
Okay, thanks for having me, Mark.
All right, take care, everybody.